So thanks for the kind introduction, Vesna, and well, thank you very much for the invitation, for having me here. It's my first time at Brown, and I haven't been. It's not been very long since I've been in the state of New England area anyway. So it's nice to get out and meet people in the neighboring universities, and this is a great occasion to be here. Interestingly, as I found out this morning, it doesn't take me much longer to get here from my house than it takes me to get to MIT in Boston. So yeah, so I plan to come back definitely. I'm looking forward to more visits. So I'm at MIT now. I've been there for slightly over 4 months, as Vesna mentioned. I'm building a new research group there. It's in experimental condensed matter physics. We do synthesis of new materials, we do scattering, we do spectroscopy, we do a lot of different things. Some of them continuing the work that I've been doing towards the end of my PhD, which was on the study of electronic orders in quantum materials, using some novel experimental techniques that have been developed in recent years, particularly this technique known as resonant X-ray scattering. So this is the outline of my talk. So this is the menu of the day. I have extended my typical talk for this colloquium to have a few additional slides in the beginning to provide more context on the concepts of emergence in quantum materials, which is one of the reasons why people in my field believe that this class of materials is particularly interesting to study from a fundamental standpoint, but also from, in principle, an applied standpoint. And then I will talk about electronic liquids and electronic crystals. Electronic crystals are what we want to study, so orders, ordered states of matter that involve the electronic degrees of freedom. And then I will talk about our experimental tools, so resonant X-ray scattering, which is essentially crystallography for electrons. And then I will focus more on the materials that is the subject of this talk, which is high-temperature superconductors, particularly the class of copper oxide. High-temperature superconductors, probably one could say the most highly studied class of superconductors to this date. And I'll do a little bit of a history of one particular theme within this class of materials, which is that of charge order, which is a very important phenomenology. And we realized in recent years that it's really universal for these materials. So it's a very fundamental phenomenon that happens in these systems. And then I will talk about recent discoveries and a little bit about future perspectives. I have a long list of acknowledgments. I won't go through everybody here, but all of these people have been instrumental one way or another for our studies. I would like at least to mention the people in Andrea Damascelli's group at UBC, where I did my PhD, and where most of the work that I'm going to present to you was done. And particularly Eduardo da Silva Neto, who did some of the work on electron-doped cuprates together with me. But he's been leading that forward and has been producing some interesting results very recently, and now he moved on to UC Davis for a faculty position. And then the very important collaboration with George Sawatsky at MIT, but also people from Max Planck Institute, Bernard Keimer's group, cuprate crystal growers from UBC, but also from other universities around the world, the group of Jenny Hoffman in Harvard for some STM, so scanning tunneling microscopy collaboration. So now let me move on to kind of start the introduction on the topics of this talk. And I guess the first slide is to provide some insights and some context on why these quantum materials are interesting, is what's special about them. In a way, we know that all materials behave according to quantum mechanics at the nanoscale, even silicon, which is regarded as a system that's certainly not a quantum material, but is a very well-known and very well-studied and probably one of the best known materials that we have at our own disposal to make devices, and it's the basis of modern electronics. However, in what we call quantum materials, we often find collective phases of matter that cannot be predicted or anticipated or even envisaged just from the nature of the individual constituents, which in the case of these materials are, let's say, electrons. So knowing how the electronic orbitals are like and knowing how the lattice, what is the lattice in this material, doesn't grant you the ability to predict the collective electronic phases that emerge in these systems. And oftentimes, this phase is translated into macroscale quantum behavior. That's why these systems are called quantum materials. And one of the most beautiful examples is that, of course, of superconductivity, which is a case of really a macroscopic quantum wave function describing your system. So we live in a complex world, and the materials that we study are certainly belong to this category. These are very complex materials, and there are two contrasting philosophies when it comes to how we approach these very complex problems. One is philosophy of reductionism, which essentially addresses the question, what are the rules of the game? So let's start from the experimental observation and try to derive the fundamental laws. And the other one is emergence, which is about trying to figure out what new phenomena arise out of basic principles, even those that cannot be predicted just from the basics and the fundamental laws of physics. And so on this side we have, again, fundamental laws, symmetries, so a few examples here. On the emergence side, we have concepts and states of matter or phenomena that cannot be easily understood from the very, very fundamental laws of physics. You can't tell from Maxwell's equations how a complex society of individuals will work. Certainly you cannot use Maxwell's equations, for instance, to predict the outcome of elections, right? So, so there is a hierarchy in science, which is such that there are different levels of complexity. And you can try to reduce everything to a set of essential laws, but ultimately you have to acknowledge the fact that at different levels in this hierarchy, there might be concepts that cannot be simply extended from the very fundamental tool set of basic physical laws. And this gives rise to very complex phenomena: superconductivity, life, human societies, and so on and so forth. So on the reductionist side, we have the fundamental building blocks, let's say the electronic orbitals. We know these very well. On the emergence, so quantum emergent properties, we have many-body phenomena, like superconductivity. So what bridges these two realms? It's mostly two things that are really critical to make the connection between, let's say, this approach, which deals with fundamental laws, and emergent quantum phenomena. And the two concepts that one needs are interactions. So you need the individual constituents, let's say the electrons in condensed matter systems, to talk to each other. If they don't talk to each other, they will never give rise to collective phases. This is like human societies will not occur if humans didn't have a way to communicate between each other. And another powerful concept is that of symmetry breaking. So you have equations, you have fundamental equations like Schrödinger's equation. And the object that defines the equation, let's say the Hamiltonian, has certain symmetries. And it's not always the case that the solutions will have the same symmetries as the Hamiltonian. Sometimes the solutions break those symmetry. And that's the very well-known phenomenon of spontaneous symmetry breaking, which is a very important concept to understand how states of matter emerge that cannot be predicted from the symmetries of the fundamental laws. So the reductionist philosophy has a very long history. It dates back to Democritus. Nothing exists except atoms and empty space. Everything else is opinion. So the idea that you can try to reduce everything to fundamental constituents, so fundamental building blocks, and understand the laws that govern the behavior of those building blocks, and reconstruct everything from that point on. And the opposite philosophy is the emergentist philosophy, which is very well captured by this manifesto paper by Philip Anderson in '72, which is actually a beautiful and very visionary article, which I really recommend you read. It's extremely interesting. And it says more is different. So broken symmetry and the nature of hierarchical structure of science. And if I have to condense the idea behind this article, there is one sentence which is particularly interesting. It says that the ability that condenses this concept, and that is that the ability to reduce everything to simple fundamental laws does not imply the ability to start from those laws and reconstruct the entire universe. So this gives rise to, this produces kind of a hierarchy in science, where you have, let's say, increasing purity going from, well, say, and this is not just physical sciences, right? You have social sciences here too. But ultimately, everything is connected. Everything cascades down to something which is more and more fundamental. But the point is that if you want to understand sociology, you cannot use the laws that condensed matter physicists or even chemists use to understand their own phenomena. You have to come up with new insights and new effective approximations and effective laws to describe the emergent phenomena that happen here and cannot be easily understood in terms of fundamental principles. So yeah, so this is in let's say, increasing purity, and sort of you're probably relieved that we are here. But even I, as a condensed matter physicist, I can only get as low as, let's say, electrons and atoms. There are people that in our departments, like high-energy physicists, and maybe there are some of you here in the audience that, of course, they look even further down at subatomic particles, at even shorter length scales, and try to understand really what's even behind electrons and atoms. So this hierarchy is inevitable when you have such a broad spectrum of complexity in natural phenomena, and which is such that new properties arise at each new level of complexity and scale. Now, for those of you who follow this kind of comic strip, this rubric, now some of you have probably noticed that there is a piece missing. So yes, so we're not at the bottom of this hierarchy. We're not at the bottom of the ladder. Now, it's a complex word, so you can go from simple entities to complex phenomena, but doing so in a purely rational and logical way and starting from these entities and reconstructing everything is a daunting task, and sometimes it requires a logical leap that's just beyond the pure inference or pure derivation. Like going from an atom, from the simple properties of an atom and electrons around it, you can't predict that certain types of atom would bind into double helical chains like DNA, and certainly just by looking at the DNA, it would be hard to predict cells. And looking at a single cell, you wouldn't be able to tell that 10 to the 20 of them, or well, maybe more, would give rise to human beings. And for human beings to complex societies and to what complex societies can achieve. So again, hierarchy of complexity, hierarchy of scales. And so where do quantum materials get in this picture? Well, the idea at this point is that we have these fundamental constituents in condensed matter. I think it's fair to say that we can start from the electrons. And the additional ingredient that we need for emergent phenomena of the kind that we observe in quantum materials is interaction. So we need these electrons to talk to each other, to form collective phases. And if you look at the Hamiltonian for a condensed matter system, that this is how it looks like. I didn't write explicitly these terms, but you can group it into a part that has kinetic energy for the ions and the electrons. And then you have potential energy. So this is the non-interacting part. This is the interacting part. This is where ions interact with each other. They form crystals that way. Or they give rise to lattice vibrations like phonons. This is ion-electrons interaction. So that's what gives rise to the properties of band states and band dispersions. And that's what electrons here participate also as an additional glue to hold atomic systems together. And then you have electron-electron Coulomb interactions, and those are the ones that are really critical especially for quantum materials, in giving that interplay, that interaction between different electronic degrees of freedom to form new quantum states that break the symmetries of the original Hamiltonian. So if we were to retain only the kinetic energy part, the non-interacting part, then everything in the universe would be in a gaseous state. Right? So it would be very easily explained with the law of ideal gases in the absence of interactions, and phenomena would be pretty predictable in a way, but also pretty boring. So you would have a very disordered state like in a gas. Now, the addition of interactions allows you to develop further states of matter. Now, one of them is a liquid state, where you have some ordering, some short-range ordering, but this state of matter hasn't fully developed long-range order. And then you can have crystals. At even lower temperatures, you can have crystals which are more highly ordered states of matter. And so this is fully disordered. Liquid has some degree of short-range order, and the crystals have long-range order, not just translational symmetry, let's say, but also they have orientational order. So the atoms are located at positions that reflect certain symmetries. So you get order from disorder when you have interactions, and the same happens for electrons. So in a material, you can have atoms but electrons, and electrons can form similar types of phases. When interactions between electrons are very small, then you have an electron gas. This is the case for certain two-dimensional systems like gallium arsenide, where you look at the energy momentum dispersion of electrons and it looks like a parabola because it just follows the law for, it's essentially just kinetic energy. So it's quadratic with momentum. The energy of electron is p squared over m. As you start adding interactions, things get more complicated. And electrons start talking to each other and they form more complex phases. One of them is, let's say, so-called Fermi liquid. I called it electron liquid here, but it's more typically known as Fermi liquid, where sometimes you get new particles that are not the original bare electrons, but they're new types of excitations that are called quasi-particles. And then at low temperatures in particular, or at strong interactions, you can get highly ordered electronic phases of matter, which are called electronic crystals. Sometimes they're called Wigner crystals. But they're basically the same as the main topic of this talk, which is charge orders. So they're phases of matter that involve the electronic degrees of freedom that form very highly ordered patterns, and they lose much of their mobility. So you get these electrons are freezing into spacious structures which are ordered and static. So this is what I'm going to talk about today, electronic crystals and how we can study them. And there are a bunch of them, a bunch of possible types of electronic crystals. So this was still a case of a lattice, so just forget about this. But look at these other three plots. So for the case of electrons, you have various degrees of freedom. You have the spin, you have the charge, and you have the orbital degrees of freedom. And all of them can form ordered patterns, can form novel exotic types of order. Antiferromagnetism is the one involving the spins, so this is a type of spin order. This is so you get a periodic arrangement of alternating, well, spins pointing in alternating directions at consecutive lattice sites. You can have an orbital order type of pattern. Well, let's say you have a lattice with 2px and 2py oxygen or whatever orbitals. And again, they form a similar pattern as in the case of the antiferromagnet, but now instead of having spins here, you have orbitals pointing in different directions, but they still form a highly ordered state, as you can see here. This is, let's say, the new unit cell in this case. You can have a charge order state where now the amount of electrons that you have at each lattice site changes as a function of the lattice, again, in a periodic way. So you have this kind of modulations of the charge, which has a given period. In this case, it has a period of 4 unit cells. Okay, so this grid is the original lattice, and you have this period of this modulation is this 4 unit cells in this direction and in this direction. So now, what we know is that different electronic orders or combinations thereof of any possible multiple types of electronic orders, they lead to different or emergent electronic phases. So what we do in condensed matter, when we study these types of quantum materials that have these fancy or exotic types of electronic orders, what we do is construct a phase diagram. So the phase diagram is 90% of the time a function of 2 experimental parameters, and 99% of the time this vertical axis is temperature. You will see that more clearly later. But we have 2 experimental parameters, and we go around in this diagram, which is it's a phase diagram. So it's so the question is, what is the electronic phase at each point in this plot? So we go here and we ask ourselves, which is the electronic phase that's more stable, has the lowest free energy, if you like, at this point, and which is the electronic phase that's more stable here. And then we construct plots that look like this. So this is the case for manganese oxide. So this is a manganese oxide perovskite. So it's a manganite crystal. This axis is temperature, as I anticipated. This axis is doping. Doping means you've added carriers in your material. So you have, and you typically do it with stoichiometry. So you have a certain stoichiometry here, and then you start adding some chemical species. In this case, you start adding strontium here. X stands as in the stoichiometry of strontium. And when you replace strontium for lanthanum, you have 2 atoms that have different oxidation states. So one of them will donate electrons or holes. And so that's how you dope your material with carriers. And this is the zoo of different electronic phases you can have in this kind of material. Ferromagnetism, antiferromagnetism, canted antiferromagnetism, charge order, type A antiferromagnetism. This is a special region where there is no long-range order. This is, again, an antiferromagnetic insulator. Some of these acronyms, I'm not even sure what they mean, to be honest with you. But the point I'm trying to make here is that it's a very rich phenomenology. So you end up with this very colorful phase diagram, typically in quantum materials, because you have multiple electronic orders. Each of them has some energy. The one that has the lowest energy typically wins, and is the one that you find experimentally to occur in your sample. As you tune experimental parameters, you tip the balance between different electronic phases or different electronic orders. And then as you change the doping, for instance, you suppress one, and one starts to appear. Another one starts to appear. And then at this point, this ferromagnetic phase is suppressed, and the canted antiferromagnetic phase starts to appear here. And then in this region, you have charge order. So you have a lot of underlying instabilities. You have a lot of possible electronic orders that in your material that are waiting to be stabilized somehow by your choice of parameter. And as you browse around in this phase diagram, you can find all sorts of possible different phenomena happening. So it's a very delicate balance, but it's also a very powerful one, because that means that with certain types of experimental parameter, you can control the quantum state of your material, and this has very, very important implications for devices, for instance. So sometimes electronic phases compete with each other, and that leads to phase segregation. So they don't like each other, but they also have very close energy. So what typically happens is that one of them will segregate in a spatial domain, and the other one will segregate in the other spatial domain. This is the case of, I think this is, again, manganites, where you have coexistence between antiferromagnetism and ferromagnetism. So they coexist, but they also compete. So they don't like to be mixed together. They're not miscible electronic phases in a way, and so they segregate each other. Now this is the concept of phase segregation is a concept that applies to many different areas, right? So we know this also in other contexts, like you have to see clearly there are two blue phases and then a lot of red. But that's so it's one of the hallmarks of complexity, the fact that you can have multiple phases that are competing. It's a consequence of the fact that you have strong interactions. Sometimes you have phase coexistence. So sometimes electronic phases reinforce each other. This is, again, the case of manganites. Manganites are a beautiful platform for this type of physics, by the way. And here you see three different electronic orders occurring simultaneously in the very same material. So in the very same spot in the phase diagram, a given doping and a given temperature, you have orbital order. So you see this alternation of these different p orbitals. Sorry, these are actually these are d orbitals of the manganese. And then you have antiferromagnetic order. You see the spins here. And you also have charge order, because you have an alternation of an oxidation state of 3+ and 4+. So you have different charge states for the manganite. They all form ordered phases. So you see, you can get this very exotic type of electronic ground states. And really, Coulomb interaction is very powerful in also not just giving you the possibility of forming these electronic orders, so giving, and enabling the electronic degrees of freedom to talk to each other, but also in the fact that it couples them together. So Coulomb interaction activates a channel for the orbital degrees of freedom to talk to the spin degrees of freedom and to talk to the charge degrees of freedom and vice versa. And this is very powerful for certain classes of materials. Let's say the magnetoelectrics, which is a class of compounds that was, I guess, discovered about 15, 16 years ago at the beginning of the 2000s, maybe end of the 90s, I'm not 100% sure. And which is a class of material where you can control the magnetism using electric fields, and you can control the electrical polarization using magnetic fields. So it's, again, very powerful for applications, especially in the field of data storage. So now the question is, how do we detect electronic crystals? Electronic crystals would form ordered patterns in real space, which means that they have certain periodicities and certain they form certain static orders in real space. So they are periodic with respect to some kind of operations. It could be a rotation, it could be a translation. When we take the Fourier transform of an object which is periodic in real space, then typically that produces peaks in reciprocal space. Those are just the Fourier harmonics in reciprocal space of something which is periodic in real space. So that's exactly what we do in our experiments. Instead of looking at the real space, which is something that some techniques do, like microscopy, we look in reciprocal space, and we focus on one of these peaks, which I'm now showing here, and we slice across it, and then we see this peak as a function of momentum. So this is momentum axis. This is some kind of intensity that we measured in the lab. And then the position of this peak, say Q star, is equal to 2 pi over the wavelength. The height, or the amplitude is proportional to the square of the order parameter. So how strong is your order? The width is proportional to the length scale of your order. So is it long-ranged? Is it short-ranged? The sharper the peak in momentum space, the more long-range your order will be because of the inverse relationship between momentum and momentum space and real space when it comes to broadening, right? Delta Q times delta R is a constant. So now we need to measure momentum. So we need somehow to transfer momentum to the sample, first of all, and measure it. And so what we do is we do scattering. So we use scattering methods, which is, I will try to explain it as simple as possible. I'm sure most of you will already know it, but it's basically like billiard physics. So we have a sample which is a big object, has a lot of mass, and has, in general, could have a large momentum. We want to just to excite a very small, we want to create a very small excitation, or we want to excite or measure or transfer a very small amount of momentum compared to the total momentum that our sample can possess. So the bottom line is that once we've transferred this momentum to the sample, there's no way we can measure the momentum of the sample directly because this is a massive object. It's not like we can put it on a scale and measure, or on a dynamometer or something, and measure how much how much momentum we've given off to it. So what we end up doing is we use a probe that has much smaller momentum than the sample has, and we look at what happens at the probe when the probe scatters from your sample. Okay, so the same as in billiard, momentum is conserved in the process. So in the beginning, momentum is only in the probe. At the end of the process, momentum is acquired by the sample and is also taken up by the scattered particle that is going in some other direction. So that's what we do, and momentum conservation is enforced in this equation here, which tells us that the momentum that we've given off to the sample is equal to the momentum of the probe, the incoming probe, minus the momentum of the outgoing probe. So if the probe doesn't interact with the sample, then its momentum will not be affected by the interaction process. So these two values will be the same, and the total transfer momentum will be 0. And if the probe interacts with the sample, then in principle we can exchange momentum with it. And to exchange different momenta, or to look at some property as a function of momentum, the only thing you need to do is you have to collect the scattered probe, the scattered particle, as a function of the angle. And by changing this angle, you will change this wave vector of the outgoing probe, and that allows you to change this Q, because typically this is fixed. A probe is anything that's willing to interact with your sample, so a lot of different particles can be used. And again, they have to carry small amount of momentum totally. This is still a non-perturbative method of probing materials. So you can have electrons, neutrons, ions, or photons. Photons are the only ones that can measure charge, spin, and orbital degrees of freedom. Neutrons can measure spins very effectively. Electrons can measure the lattice or the charge very effectively, but the only ones that can probe all of these degrees of freedom really are photons. There is only one problem. That's typically, when you do X-ray diffraction, which is scattering using photons, short wavelength photons, which are X-rays, typically you measure the lattice. And why is that? Well, that's not because the photons interact with the atoms. The photons actually always interact with the electrons. But an atom is made of an atom has a certain number of electrons surrounding it, and most of those electrons are core electrons. And there are only a few valence electrons, which are the electrons that are close to the Fermi level in your material. So when we scatter off the electrons in a given system, in a given crystal, then we're mostly scattering off of the core electrons. And the contrast from the valence electrons, which are the ones that we're interested in, because they're the ones that can talk to each other and form these special types of electronic orders, that's extremely small, to the point that it's non-detectable. So when you do crystallography, you measure the atomic lattice. And this is a problem, because now we're interested in measuring not the atomic degrees of freedom, or the atomic lattice. We're interested in measuring the electronic degrees of freedom. So we play a trick. We go to certain resonances. So we change the photon energy of the X-rays. And at certain special energies, you increase the sensitivity to certain electronic final states that correspond to certain transitions from core level to valence electrons in materials. And they all have different energies. So let's say copper. This is the energy for a transition between a 2p core level and a 3d valence electron. And if I tune my energy there, I increase my sensitivity by something which can be of the order of 1,000-fold to the 3d valence electrons of copper. If I go to nickel and I do the same type of transition from a 2d from a 2d core electron to a 3d valence to a 3d conduction electron, then I'm looking at the same thing, but now the energy is slightly different because of the binding energy of the 2p core hole. The core electron is changed. So all of these different elements have different resonances that occur at different energies. And so with resonance scattering, which is what I'm going to talk about today, we can do essentially site-selective crystallography. And not only that, so not only we can focus on certain atomic species in our material, and specifically I'm going to talk about cuprates. So we're going to focus on the copper-oxygen plane. So we're going to work at the resonance of copper atoms. But we can also enhance the contrast from just the valence or conduction electrons in my material, as opposed to regular crystallography where the core electrons will dominate. And we're not interested in the core electrons. We're interested in the valence electrons. So this is the photon energy dependence of scattering from the core electrons or regular diffraction. It's pretty much constant versus photon energy. And when we do resonance scattering instead, we have a very strong enhancement at certain energies which correspond to the resonances in your material. And this is so strong that a single electron or a single hole in your material at resonance can scatter as strongly as 82 electrons, which is the scattering strength of a lead atom, which is a lot. So how do we do these experiments? And then I probably have to rush a little bit. So this is incoming photons, incoming X-rays. This is your sample. And then you collect the scattered X-rays with a detector that can move as a function of so it can move in angle in a diffractometer. So this is the inside view of the diffractometer. Okay, the detectors are here. They can move on a rotating arm. The sample is here. It's fixed in the center of the diffractometer, but you can rotate its angle. And as we rotate both the angle of the sample and the angle of the photon detector, then we can change the wave vector q, and we can change the projection of the wave vector q on the crystallographic axis of the sample. So we can explore this way by using these two angular axes. We can explore the momentum space of the sample. So this is the inside view of the diffractometer. It's a soft X-ray diffractometer. You have to work in ultra-high vacuum, unfortunately, because that creates a lot of complications, but it can be done. And this is the incoming photons come from here. So this is a long tube that has to be, of course, has to be connected to some source of X-rays that has to be tunable. So because you want to work at certain resonances. So you need a synchrotron. So this is not something we can do in the lab. You have to go to special facilities where we can do these kinds of experiments. Now, fortunately, there is a lot of choice in the world, so you can do it in a bunch of different places. And now that we're in Boston, we were start to look to go, especially here at Brookhaven National Lab, which is the nearby facility, which is actually one of the newest synchrotrons that has been built and one of the highest performing in the world right now. So we're very excited at doing science there. There are certain choices of synchrotrons that are better than others. Like California is definitely a good choice. But then you don't do a lot of science there when you have this view outside. Whereas if you go in Canada, well, you're freezing yourself, but at least you're very productive because you don't want to get outside. So it works. Depends what you're looking for for your experiment. But so there's a lot of choice in the world. So now let me get to the subject of this talk, the cuprates. So high temperature superconductor. This is the structure of the cuprate. So you can have different compounds, but the take-home message of this slide is that the fundamental ingredient in all these structures is the presence of these copper-oxygen planes, which are the crystallographic places in this complicated unit cell where all the interesting phenomena happens, in particular superconductivity. And this is because all of the low-energy electronic states live in these planes. Okay, so the electronic states are the copper 3d orbitals and the oxygen 2p orbitals that are hybridized with each other, and they form the low energy bands that are the ones out of which superconductivity emerges. And these are the highest superconductors known to date, with the exception of now hydrogen sulfide, which has been discovered to be superconducting at about 100 billion atmospheres or something. So let's say this is still at ambient pressure. These are still the best superconductor in the world, but there hasn't been much progress since the 90s. So it's natural that now people are looking in different directions. And this is the phase diagram of the cuprates. So we have antiferromagnetism here. So this is the this green dome is antiferromagnetism. This is Fermi liquid. So here you have an electronic liquid state. So there's no electronic crystal. There's no particular fancy electronic phase here. This is still an interesting state to study, but there's no electronic order down here. This is a superconducting dome, and this is, sorry, I forgot to mention, this is a function of doping and temperature. Okay, so superconductivity happens about 5%. This is the case of one particular compound, which is called YBCO, but the shape of the phase diagram is similar for all of them. And then typically superconducting dome ends around 25% in the so-called overdoped region. So this is overdoped region, underdoped, and this is optimally doped. This is a Mott insulator, which means that you have one electron per copper site. Electrons cannot move, because as soon as one electron moves to the neighboring site, then you have two electrons on the same side. The interactions are very strong. The energy of that configuration is very large, and that hopping process is effectively forbidden. So there is one electron per copper site, nothing happens. This is an insulating state. It's very well known, and it's a strongly correlated state of matter. On this end, you have doped sufficient number of holes that they're free to move around in a liquid-like state. So you have a good conductor down here. And here in the middle, which is the underdoped region, then you have some carriers, you have some holes, you've doped some holes there, but not enough to create this electron liquid. And what happens here is that these holes actually crystallize into static orders, which are given as a form of kind of modulation of the charge density, okay? So they're not as extreme as this case, where you have one electron per copper site. In this case, you have kind of a more gradual modulation of the charge density, but still a periodic object and static. And this is called charge order, which is what I'm going to talk about today. And charge order is relevant for the cuprates because you go from, so this is the superfluid state that you have in the superconductor, where electrons have to be mobile. This is, actually holes have to be mobile. This is the state you have in an electron crystal, where these holes are actually crystallized at particular positions that they don't want to move. So these two states are naturally in competition, and this has been proven experimentally to be the case in the cuprate. So charge order is very relevant because it's an antagonist to superconductivity. So it's important to study its properties, which we did. Well, we and a bunch of other people in the world did, and we kind of had the opportunity to summarize this in a review paper that appeared this year. So I'm tentatively following the narrative of this paper now in the second part of my talk, where I'm going to discuss specifically the phenomenology of charge order in the cuprate, with an emphasis on the use of resonant X-ray scattering methods to measure this charge order in reciprocal space. So, and I'll do this in a strange way, in the sense that I'll start from the very end of the story, which is the charge order temperature map as we know it today. So at this point, I think this requires a bit of an explanation of what this is. So this is still a phase diagram in a way. It's not properly a phase diagram because I'm not drawing phases here. What I'm drawing is the onset temperature of charge order of this electronic crystal state as a function of doping. So this is a superconducting dome. This is the antiferromagnet. And now we have a new electronic order here in this region between, let's say, 6% and 16, 17%. In all different cuprate compounds. This is really universal. This is one of the big discoveries of these last few years. And it appears at different temperatures for different compounds, which is not particularly surprising. That is also the case for superconductivity, for instance. But in all cases, it's maximum around this kind of magical doping of 12%. And this is something that's not yet, the reason for that is not yet very well understood. And this is a similar map as a function, again, plotted versus this kind of phase diagram, but again, as a function of doping. But now I'm plotting the wave vector, which is 2 pi over lambda. So it's 2 pi over the period of charge order. So 0.33 means a period of, and it's in reciprocal lattice units. So 0.33 means a period of 1 over a period of 3. So the wave vector is 1 over 3, 0.33. which means a spatial period of 3. Here, 0.25 means 1 over 4, so that's a spatial period of 4. So that tells you what is the wavelength of this wave-like modulation of the electronic density in your superconductor. And it changes in different ways for different compounds. And this is something that we don't yet understand. So it's there everywhere for all possible cuprates, again, in the same range of dopings. But in some of them has a given behavior as a function of doping, and in other ones has an opposite behavior as a function of doping. So it seems like it's universal, but it also behaves a bit differently in different classes of compounds. OK. So the question is, how did we get there, and what new things have we learned on this phenomenology of charge order in the case of superconductors? So the first detection of charge order was actually 20 years ago, 21 years ago, not far from here in Brookhaven, by John Tranquata using neutron scattering. They found this pattern of, so these black things are holes, and the rest are electrons. So there are basically one-dimensional rivers of charge, or stripes, that separate domains with antiferromagnetism. Okay, and this kind of stripes are separated by four lattice parameters. Okay, so this is not quite a sinusoidal modulation of the charge density. It's more like it's more of a kind of a phase separation between a region that has holes and a region that has electrons here. And this was the first detection ever in the cuprates of these holes crystallizing into periodic patterns, this kind of stripes here. This was later discovered also using STM in the early 2000s, and then more recently it was discovered in the only compound where one of the compounds where this charge order was never proven to be existent, to be there. And this was an important discovery because it was the first time that it was suggested that charge order could be a universal property for the physics of high-temperature superconductors. And the first detection was using NMR. Sorry, the very first suggestion of charge order was using quantum oscillations. This is a very fancy technique that uses high magnetic fields to cause oscillations in the transport properties from which you can indirectly detect the presence of electronic orders. I don't want to bore you on that, so I'll not touch on that. But more recently, it was shown using NMR that essentially there are inequivalent sites in your copper-oxygen planes at high magnetic fields. And the only way you can have inequivalent sites, so if there are inequivalent sites that should be equivalent, which you can see through the presence of different transition lines, nuclear transition lines, the only way you can have inequivalent sites if you have a charge order that distinguishes the electronic states at different copper or oxygen sites. And more recently, charge order was then found in the same compound, YBCO, using resonant diffraction and also non-resonant diffraction here. So you see this peak. This looks like the peak that I showed before at the introduction in the first few slides. So you have a peak at a wave vector of about 0.31, which corresponds to about 3 unit cells of wavelength in real space. And you can see this is the intensity of charge order. And it grows, it increases. And when you reach the superconducting temperature, it starts to drop. And this is a very direct indication that superconductivity and charge order are in competition. So when superconductivity kicks in, charge order gets weakened. So the amplitude or the strength of charge order goes down. We studied this in one of the few missing compounds, which was bismuth-2,201, which was one of the bismuth-based cuprates. And we found charge order to be present there too, at a wave vector of 0.25 reciprocal lattice units, so with a periodicity of about 4 unit cells in real space. Okay, it's a very hard measurement. As you can see, this is a very weak peak in reciprocal space. Typically, these things, if you do Bragg crystallography, if you do crystallography in general, these are extremely sharp. This is very broad, and it's very hard to detect, but it's there. So it's a challenging experiment, but it's there. And the only way to see it is if you tune yourself to the resonance. If I move my photon energy away from the resonance is this blue curve, okay? And these are the points where I do my measurements. So this is the amplitude of this peak as a function of the photon energy, these red points. If I am right at the resonance, I see this peak has a finite intensity. But if I move away from the resonance, I become completely blind to the presence of these charge modulations. So being able to tune your photon energy makes you, increases your sensitivity to things that otherwise you cannot see, you cannot detect doing conventional crystallography. So we studied this as a function of temperature, and we realized that the point where in the temperatures where charge order starts, where charge order begins, so where it appears as a function of doping and temperature, so this is the phase diagram, they seem to be very close to the onset of a different electronic phase, which is called the pseudogap in the cuprates, and some of you might have heard about it, but it's a very exotic and very mysterious type of electronic phase where people have found all sorts of broken symmetries and now also charge order as kind of a breaking of translational symmetry. This is not a very well understood phenomenon for the physics of cuprates. And what we've seen here, what we've noticed is that charge order seems to appear contextually with this pseudogap phase. And we did this measurement using scanning tunneling microscopy. And if you take the Fourier transform of the real space data from scanning tunneling microscopy, then you see a peak, which is at exactly the same position as the peak we measure in scattering as a function of momentum. So this confirms that this phenomenon, as was observed previously in real space, is the same as we can observe now in reciprocal space. This has been seen since in other compounds, so it has now been proven to be a really universal phenomenon for the physics of the cuprates. And one point I would like to make is that when you do crystallography, when you look at things as in momentum space, you typically look for things that are ordered. So things that are in real space, they form very well-defined, long-range ordered types of patterns, like atoms in a crystal. So you expect something like this, right? So you expect that the length scale over which the function that you're measuring, say the atomic density or the electronic density, the length scale over which that is coherent with itself, so the correlation length, is very long. And that is the case for certain types of charge order in the cuprates. And that's certainly the case when you do regular crystallography, because atoms have a very long-range coherence. Atomic lattices have a very long-range coherence. But as we went to study YBCO, one of the other cuprate compounds, or BISCO-2201, which is one of these bismuth-based compounds, we realized that basically we're looking at objects which are periodic in real space, but they have a correlation length which is of the order of a few wavelengths. So it's extremely short. So this thing oscillates for a few wavelengths, and then its phase slips. And so it doesn't look the same as the original oscillation. Okay, so the length scale over which these oscillations of the charge density remain coherent with themselves is only a few wavelengths. So it's extremely short-ranged. It's hardly an electronic crystal, you would say. But it still retains some degree of periodicity in real space, because we see a peak in reciprocal space, even though, as you can see from here, it is very broad compared to, let's say, this very sharp peak. So now we ask ourselves the question, what else can we learn from resonant X-ray scattering? This is the acronym. So let me go back to the slide that I had previously.
Are you able to learn something from the shape of the peak as well?
Yes, that's what I'm going to talk about now. No, that was a great introduction, actually. So yes, absolutely. And we thought about this because we realized at some point that when we measure these features in reciprocal space by slicing across the peak, then we lose a lot of information. These peaks are not defined in one-dimensional momentum space. The momentum space is three-dimensional because our material is three-dimensional, right? So these peaks are really kind of spheroids or ellipsoids in reciprocal space, and we're only slicing along one direction, and we're only taking very, very little information out of the full information that's available in reciprocal space. Ultimately, this full information that's available in reciprocal space is closely connected to the real space structure of these ordered states, because what we measure in reciprocal space is nothing but the power spectrum of the Fourier transform of this electronic density in reciprocal space. So let's now talk about the, let's say, two-dimensional structure of charge order. And one thing we know is that charge order is really two-dimensional, so there is no coherence along the out-of-plane direction. So we can say that in a way, the only two variables that matter in reciprocal space are the ones that are parallel to the copper-oxygen planes, because charge order is really a two-dimensional phenomenon for the copper-oxygen planes. So let me take a stripy domain. This is a circular domain with stripes. So if I take the Fourier transform of this guy, so this is the wavelength, let's say, so these are the crests of my sinusoidal kind of charge modulation. The crests are propagating in the horizontal direction, so I only have a peak along the qx reciprocal axis, right? This makes sense. I have no peak along qy. And I have a given broadening in reciprocal space, which reflects the fact that this domain has a coherence, a real space coherence, which is only, let's say, a given number of wavelengths. And the broadening in reciprocal space is, as we know, inversely proportional to the coherence in real space. Okay, so if this is the coherence length along x and this is the coherence length along y, then the broadening, vertical broadening here is 1 over this coherence length and 1 over the coherence length along x for the broadening along qx. So now if I shrink this domain along the x direction, what happens is that because of this relationship between the momentum space and the real space broadening, or the momentum space and the real space coherence, this peak will become broader in the qx direction in reciprocal space, because as the domain has become narrower in the x direction in real space. So if I add another component now, which unfortunately you cannot see very well, and it doesn't come out very well on this projector, but I've just added another modulation in the vertical direction. So these are kind of horizontal stripes that are propagating along the vertical direction. Then that creates another peak here along the qy axis. And this peak has to have the same shape as this peak in reciprocal space, because they share the same domain structure here. They share the same correlation length. So the broadenings have to be the same. So if you have two orders present, two modulations along two directions present at the same time, then they should have the same structure in reciprocal space along one reciprocal axis and the other reciprocal axis. So we went ahead and did this kind of experiment in the cuprates. So we sought after resolving the two-dimensional structure of these diffraction peaks that we can see with resonant scattering. So we came up with a name for it, but don't focus on that. It's actually T-Rex if you read it, but it's fine. But it's in a way tomography, right? So we're reconstructing a higher dimensional object by taking lower dimensional slices through it. In this case, we take one-dimensional slices through this two-dimensional peak, and we reconstruct its shape. We have to use a special geometry for doing this. I'm not going to talk about it in detail, but we can do it, bottom line. So we can get these different profiles, and we can reconstruct the shape of this peak in reciprocal space. And this is one of the cuprate samples. It's called YBCO sample. It's one of the cuprate compounds as a function of doping. This is 10% holes per copper, 12%, and 13%. And we look at the shape of these peaks in reciprocal space along one reciprocal axis, which is H or QX, they're the same thing, and along the other reciprocal axis, K or QY. And we realize that these shapes are not the same. So they violate a symmetry which is to be expected if you have two modulations, one along one direction and one along the other direction, present at the same time in the same spatial regions. If that were to be the case, then you would expect these two peaks to have the same structure, but actually they have the opposite structure. As you can see, the anisotropies are pointing along different directions. So this is evidence that actually at the local scale, the order is not bidirectional, but it's unidirectional. So you have stripes at the local scale. Like globally, you have both of them. But at local scales, you have domains. Your charge order state is broken into domains that are locally unidirectional. And we studied this as a function of temperature, but I don't have time to talk about it, so let me skip it. Yes, so by resolving the two-dimensional peak structure in reciprocal space, we can basically tell that there is a broken symmetry at the local scale, and these domains are really stripy. They're not checkerboard-like, again, locally. So then we went ahead and we did something else with this resonance scattering measurements, and we looked at the inner symmetry of charge order. So what do I mean by inner symmetry of charge order? So this is the copper-oxygen plane. This is one particular direction in the copper-oxygen plane. These red orbitals are copper 3D orbitals. These yellow ones are oxygen 2p. These are the states that are the basis for the electronic structure of cuprates. Now, formally, charge order is, again, as I explained before, a modulation of the charge density as a function of your lattice position. But really, you have three different types of orbitals here, right? You have copper 3d, oxygen 2px, and oxygen 2py. So there is a little bit more structure than this simple kind of picture of an oscillating charge here, because that charge can be on three different orbitals. So you can have more complicated patterns there, and I'm going to discuss this in a minute. Before I discuss that, I want to make one important point, that if you have orbital patterns where the charge is not changing, but the direction of your orbitals is changing as a function of your lattice, then you cannot measure them with diffraction, but you can measure them with resonant scattering. And the reason is that diffraction and scattering have two different quantum mechanical formula, quantum mechanical cross-sections. What diffraction measures is something which is proportional to a quantity, which is technically called a form factor, but in the case of diffraction, this is proportional to the Fourier transform of the total charge at a given atomic site. Okay, so just remember this. This is basically a Fourier series, and the term in this Fourier series is the Fourier transform of the electronic density at a particular site. But for small q, which is what we're looking at here, this kind of converges to the total charge at that atom. So in the case of copper, that would be 29. In the case of oxygen, that would be, I guess, 8, and so on and so forth. In resonant scattering, the quantity we measure here is a tensor, and that tensor reflects the orientational local properties of the orbitals that are involved in that transition process. So this tensor for this vertically pointing orbital is different than the tensor for this horizontally pointing orbital. So what we do now, we have to take this summation here for the case of diffraction and scattering, and what I need here is I need this phase factor, which is this e to the iq dot r. So I have this period 2 orbital order, which means that your q is 2 pi over 2. So here is this phase factor, here is 1, here is -1, here is 1, here is -1. Okay, that's the interference factor between different atoms that give you the diffraction process. Total amount of charge here is the same, because there is 1 electron here, 1 electron here, 1 electron here, 1 electron here. But this form factor that enters only the resonant X-ray cross-section is different from this site, let's say the A site and the B site, because it reflects the orientational properties of the orbitals, not just the total amount of charge. So if I take this summation here, evaluate it for this kind of, for these 4 orbitals here, then I get q times 1 minus 1 plus 1 minus 1, because these are the phase factor that enter here, right? This gives me 0, so I cannot see this with diffraction, even though it's an ordered arrangement of orbitals. If I do this with scattering instead, well, these two lattice sites have a phase factor of 1, and they have the same form factor, Fa. These two sites here have a phase factor of -1, and they have a different form factor, Fb. So in the end, if you take this summation, you get 2 times Fa minus Fb, which is different from 0 because these two tensors are different. So with resonant X-ray scattering, you can measure orbital patterns like this. And this is exactly what we did in the cuprates, and now I really have to go a bit fast. How much time do I have? Like, am I completely out of time? I have some injury time? Okay. No, thanks. Sorry about that. I'll wrap up. So as I mentioned before, we have 3 different types of orbitals. So we can have 3 possible different orbital patterns for charge order. One where all the charges are on the lattice, on the copper site. So charges are only on copper 3d electrons. Copper 3d holes. They don't go on oxygen 2p states. And this is what we call site order. And then we can have 2 different types of bond order. Bond meaning that the charge sits in the bond between the copper, so it sits on the oxygen 2p states. And you can have one where the maximum of the charge on the horizontal oxygen 2p states is in phase with the charge on the horizontal 2py state, on the oxygen 2py states. So it's maximum here, and then it oscillates, but it's always maximum together, right, or minimum together. In the D-wave bond type of order, then they're out of phase. So when it's maximum on the oxygen 2p axis, minimum oxygen 2py, and then it oscillates back and forth, right? It goes minimum on 2px, maximum on 2py, and it goes, it oscillates back and forth as a function of the lattice position. Turns out you can map this out onto a quantity which in resonant scattering we call the scattering tensor. It's related to that tensorial quantity, the form factor that I introduced before. But it turns out we can map these three representations exactly onto three different representations of this scattering tensor. And this is where the beauty of resonant scattering comes in. We can measure this tensor by projecting it onto different polarization state of the incoming and outgoing X-ray photons. And we did this measurement. The way we do it actually is we rotate the polarization around the crystallographic axis, and then we measure how much the signal changes as we rotate the incoming polarization. Unfortunately, we cannot yet control or measure the outgoing polarization, but we're in the stage of developing tools to do that. But what we can do is we can rotate the incoming polarization and basically project different components of these tensors and then look at how the total signal is modulated in intensity. And as you can see, there's a clear modulation as we sweep the angle of the polarization with respect to the crystallographic axis. And if we model this change in the intensity as a function of this azimuthal angle of the polarization, which measures different components of that scattering tensor, then we see a fundamental asymmetry here in the sense that the minimum in this change of the intensity is displaced away from 90 degrees, which would be the symmetric situation going from 0 to 180 degrees. So it breaks some kind of local fourfold symmetry, and the conclusion is that we have this type of D-wave bond order, which clearly breaks this symmetry locally. So it clearly breaks this fourfold symmetry. And you can see it quite clearly in this diagram here. So this was then later discovered in other compounds. So this study a whole new kind of direction of study on the local symmetry of charge order. And there is a whole new chapter of studies of electron-doped cuprates, which I'm not going to discuss because I don't have time. But basically, we found charge order there as well. So it's really universal on all cuprates, not just hole-doped cuprates, but also electron-doped cuprates. So we find it there for a bunch of different doping levels. And okay, so it's universal. It's everywhere. So I'm just going to conclude with future opportunities for this technique. And one of them is to do diffraction, or resonant diffraction, so look at electronic orders, but now with an X-ray beam which has been focused to a few tens of nanometers in size, using special diffractive optics that can do that. Let's say we have those optics. Actually, we actually do have those optics. So we can focus the X-ray beam down to a few tens of nanometers. And then we can sweep it across the sample and look at whether there is any inhomogeneity of your state, of your electronic order, due perhaps to that kind of phase competition that I introduced previously, right? That drives phase segregation. So there are regions of your sample that have weaker charge order, other regions of your samples that are stronger charge order. And this was done recently using diffraction, actually. So it shows that there is a very rich phenomenology in real space happening. So this is interesting because now we do diffraction. So we look at orders in reciprocal space. We measure how strong they are and how coherent they are in reciprocal space, but still with the ability of scanning them over mesoscopically small nanoscopic regions of your sample, but over mesoscopic fields of view of a few microns. And the other possibility is that of doing what I was showing before, so using these azimuthal scans by scanning the polarization around, but now with the added capability of also projecting the outgoing polarization to get an even better understanding of the local orbital symmetry of these ordered states in these quantum materials, not just cuprates, but now we're exploring nickelates, we're looking at manganites. So we're using these new tools to look back at materials that had been studied previously, but not with the experimental suite that we have right now. And now there are beamlines. As we're collaborating with these guys in particular in Brookhaven. We're building this setup for that beamline. So this is going to be very interesting. This is going to be very interesting. And you can only do it in one place in the world right now because you need a coherent source of X-rays. So I want to conclude with kind of some commercial or some advertisement on. So this is the website of my new group. We're recruiting new students. We're 3 people now. I have 2 students in my group. There are a few postdocs coming in next year. So the group is getting populated. We're kind of building the lab. And as I mentioned in the beginning, we're going to do synthesis, spectroscopy, and scattering on a bunch of different materials platforms, going from oxides, transition metal oxide, arsenides, chalcogenides, a bunch of quantum materials, so all materials that have one way or another, bring in strong electronic correlations and exotic electronic phases. And then we use light scattering. So this could be optical, like Raman scattering, or X-ray. And we do both elastic scattering to look at static orders, but also do inelastic scattering. So when you not only transfer momentum to the sample, but you also transfer energy to look for the momentum energy structure of excitations in your material. And we like to do this as a bunch of different experimental parameters because we like to explore the phase diagram along a bunch of different experimental axes. So with that, I leave you with a general summary of charge ordering the cuprates as we know to this date. And with that, I thank you very much for your attention, and sorry for the overtime. Typically, you track that as a function of some experimental parameters like doping, or temperature, or pressure, or strain, or magnetic field, to look at how that particular electronic order is affected by these experimental parameters. So is it suppressed? Is it weakened? Is it enhanced? The amplitude basically gives you a measure of the global order parameter that's associated to that particular electronic order. So by tracking the amplitude as a function of a bunch of different experimental parameters, you can look at how that particular electronic order behaves in comparison to other electronic phases that you might have studied with transport or other tools.
Are these really small amplitude oscillations in charge density, or how large are they?
It's hard to tell because we don't really probe the charge directly. There's no technique that can probe the charge directly, right? So that's not an observable for our method. We can infer that by some special methods, like by comparing that to how strong the scattering is for some Bragg reflections, for instance, that have a very well-known structure factor. But it's still very hard. Estimates of this kind have been done for other cuprates where the peaks are much sharper, and so there's much better control over the total area, the total amplitude of the order parameter, and it's been estimated that the amplitude of the charge oscillation, but again, it's an estimate, is of the order of 0.04 electrons. Keep in mind that there are 0.12 holes per copper, so you can't oscillate more than half of that, right? So it's estimated to be about 0.04. Yeah, the relative changes, yes. But absolute estimates of how much charge is modulating, that's much harder. We can tell how coherent it is in real space. So what's the correlation length? That we can easily tell. But yeah.
So for those strike domains you show, you look at the center of the sample. So what happens if you move your probe beams to the edges of the sample?
Well, we haven't tried that, to be honest, but for that measurement, that's a macroscopic measurement. So the X-ray footprint, the footprint of the X-ray beam is of the order of 100 to 200 microns. So I don't know how big that edge would be, but if what defines that edge is something of the order of 10 nanometers or something from the actual physical edge of the sample, then we wouldn't even see that. You really need a nanoscopic tool like the one we're developing to be able to do that measurement, not only as a function, not only in momentum space, but also as a function of real space, and looking for any real space inhomogeneity, or perhaps any edge type of physics, right? So we cannot assess that right now, but with these tools we're developing, potentially we can look into those things. But do you expect something to happen at the edges?
Yeah, suppose if we pattern the sample into some kind of, let's say, hexagonal patterns.
Oh. Well, if you can pattern it at a nanoscale, maybe, yes. I mean, correlation length is of the order of, in the best case scenario, 100 angstrom, so 10 nanometers in the best case scenario. So But then you could affect other properties like superconductivity, right? And that has a feedback on charge order. So I'm thinking, if you think more broadly, something could happen.
May also change your phase time.
That's right. That's the point. So you would have to change everything, and therefore charge order will respond somehow to.
But you can consider those things that Alperin does with superfluid helium-3 inside a material.
Hydrogel or charge order aerogel equivalent.
We're thinking of doing some devices where we inject currents to suppress superconductivity, because so to get into the flux phase, or actually flux flow phase, I think it's called. So not quite into the depairing regime, but let's say injecting electrical currents as opposed to using a high magnetic field to suppress superconductivity, and see what the impact is on charge order. Unfortunately, you have to get to very high magnetic fields to do something dramatic to charge order. You have to go above 16 Tesla, and you cannot do that with soft X-rays. You simply cannot do that. But you could do it with current. So you can make a small device that has a small channel, perhaps a thin film, where you can inject the current, and then the current density would be very high because you have a very small cross-section in a thin film. And then with a nanometric beam, then you can look into this channel where you have a large current density and perhaps see what happens now that you've suppressed superconductivity with large currents. That's one idea that we have.
You mentioned the antagonism between charge ordering and superconductivity.
Yes.
Is there a possibility of a supersolid type phase where you have coexistence of the two orders?
Yes, so they definitely coexist, because even in the superconducting phase, charge order is not completely suppressed, it's partially suppressed. So this is the concept of superstripes that some people have proposed. There's an Italian person that has come up with this, with some theories and some kind of experimental proposals for this type of, I guess you can call it like a super solid type of phase. Yes, but that's exactly why we're developing these nano tools. So if there are pockets of charge order that are somehow disconnected and then supercurrents flow around them, then we cannot tell it from our measurements, because those are we look at microscopic features by using macroscopic probes. But if we use nanoscopic probes, then we might be able to image single domains and really tell what's the real space texture of charge order and see what the connectivity of that texture is. And that gives a lot of information on whether, let's say, is there some kind of percolative regime of some kind that's expected to be reached at some point, or in certain cuprates, superconductivity is never fully suppressed, even in the regime where charge order is strongest, right? You have a dip in the TC, but it doesn't go to zero. But in some other cuprates, it does go to zero. So what is the impact of charge order there, and why does superconductivity go to zero? Is that because the topology of the superconducting region is changed so dramatically, like in the case of colossal magnetoresistive manganites, that supercurrents cannot flow freely anymore? Or is it because the C-axis coherence is suppressed? So there are a lot of these scientific questions that hopefully this new experimental instruments will be able to address. Yes, you can look at charge. You can. That's right. You can. That's right. You can only look at charge order. Yes.
Or if you sample just whatever you're looking at, the resonance peak goes down anyway because the electrons are paired now. Well, no, this is so much high energy that it doesn't matter. Right?
No,
So you're really just sensitive to charge.
Mostly, yeah, uniquely, yes. Well, not sensitive to superconductivity. Let's put it this way. One day, maybe the energy resolution will become so good that you can see actually the superconducting gap as a suppression of a spectral wave when you do an inelastic resonant inelastic X-ray scattering measurement. Now, just to give you the idea, the resolution there is 38 millielectron volt in the best case scenario. So people are starting to inquire about whether you can see actually the superconducting gap in the energy channel as a suppressed spectral wave below the TC.